For the past 12 months, I've been running my own home lab, using it to self-host a number of different software and services. My original setup was a highly available 4-node Kubernetes cluster powered by K3s. And whilst I've been really happy with this setup, I definitely made some mistakes at the beginning, ones that I would change if I was to rebuild my cluster from scratch. And so I decided to do just that, taking what I had learned and building what I think is the perfect home lab. To begin, I decided to write down my thoughts about what I wanted my next setup to be. Just as before, I wanted my home lab to be a highly available Kubernetes cluster. However, this time I wanted it to be 3 nodes instead of the 4 that it currently was. This would help to simplify my setup as well as saving power and reducing costs. Additionally, I wanted each node to have 32 gigs of memory and 2 terabytes of storage, as this would enable me to run more services on each node. When it came to networking, I wanted each node to at least have a single 2.5 gigabit Ethernet port, which would be plenty enough for my home network. And last but certainly not least, I wanted to make sure that an individual node would use less than 20 watts when idle. This would help to prevent heat, noise, and to save on energy costs. As well as saving energy, however, the CPU also had to be capable to handle any tasks I threw at it. With my hardware requirements defined, I went about searching for a viable option, which ended up being the Beelink EQ12, which either met or exceeded these specifications. The EQ12 comes with the Intel N100 CPU, which is incredibly low powered, causing the machine to use 11 watts when idle and 23 watts when under load. Despite this efficiency, however, the N100 is still rather performant, with an iGPU that supports most modern media codecs. When it comes to networking, the EQ12 comes with dual 2.5 gigabit Ethernet ports, which again is more than I was looking for. However, by default, the EQ12 only comes with 16 gigabytes of RAM and 500 gigabytes of storage. Fortunately, it's pretty simple to upgrade both of these components. And even though Intel's own website says that the N100 only supports 16 gigs of memory, I was able to install and use 32. So I went and ordered the following 32 gigs of RAM and a 2 terabyte SSD from Amazon. If you're interested in buying the same hardware yourself, I have a link to everything I bought in the description down below. In total, this cost me about $1,400. If you're just getting started with home labs, then I wouldn't recommend spending this sort of money. Instead, I recommend using an old laptop or any other hardware you may have lying around. Once everything had arrived, the next thing to do was to install my upgraded components. This is pretty easy to do on the EQ12. I began by removing the bottom plate of the case, which involves removing 4 screws and then pulling up the plastic tab. With the base removed, I was at the enclosure for installing a 2.5-inch SATA drive. However, to have access to both the memory and SSD, I needed to remove this enclosure as well. In order to do so, I had to remove another 3 screws, 2 of which were pretty hard to find. However, one silver lining was that all of these screws were the exact same size, so I didn't have to worry too much about getting these jumbled up. After removing these 3 screws, I then went about lifting up the SATA enclosure very gently, as there are a couple of cables attaching it to the main board. The first of these is a 4-pin header for the fan, which I went about detaching. Once it was detached, I could then move the enclosure out of the way without needing to remove the second cable. With that, I now had access to the components I wanted to upgrade. So I began by first upgrading the system's memory, removing the existing 16 gigabytes and replacing it with a cool 32. After replacing the memory, I went about replacing the SSD, first removing the screw keeping it in place, then replacing the stick itself and screwing the new one back in. Once both of the upgraded components were installed, I went about putting the machine back together, first reattaching the fan cable before screwing in the 2.5 SATA drive enclosure. Once that was reattached, I could then put back on the bottom plate and add in the remaining 4 screws. Then all that remained was to repeat the process for the other 2 machines. With the upgrades installed, the hardware tasks were now complete. Next, it was time to install the software, i.e. installing an operating system. But which one was I going to choose? For my initial home lab, I had chosen to go with Ubuntu Server, and whilst this worked, it was a little bit tedious to go through the setup process for each machine. So this time I wanted to go with a more declarative approach, which led me to 2 different options. The first was a distro called Talos Linux, which is an immutable minimal distro designed for Kubernetes. Talos does look pretty interesting, and I think I'll do a video on it in the future. However, I hadn't used Talos before, and for this project I wanted to go with something a little more familiar. So I decided to go with my second option, Nix OS, which has quickly become a favorite of mine in 2024, after having used it on both of my framework laptops. To make the process of installing Nix OS even easier, I decided to use Nix OS Anywhere, which enables you to remotely install Nix OS using SSH. In order to do so, I first needed a copy of the Nix OS installer flashed onto a USB drive. And so I downloaded the ISO from the Nix OS website, plugged in my trusty Samsung Fit, and decided I wanted to live on the edge and use the ever-risky dd command to flash the image. Once it was done, I ejected the USB drive and began setting up my first node for installation, plugging in the necessary cables before inserting the installer and powering the device on. As this device was fresh, it booted straight into the installer without me having to perform any interception. Once the installer was loaded, I first set a password using the passwd command. This would enable me to use SSH, which is required for Nix OS Anywhere. Once the password was set, I then obtained the IP address using the ipadder command. With both the password set and the IP address in hand, I was then able to install my Nix OS configuration using Nix OS Anywhere. In order to do so, the source machine needs to have the Nix package manager installed on it. As I was using Arch, by the way, I installed this using Pacman. Once it was installed, I then went about writing my Nix OS configuration, adapting it from one I wrote on stream a couple of months ago. If you're interested in using this configuration yourself, it's available on GitHub and the link is in the description down below. If you do end up using this configuration for your own homelab cluster, the main thing you'll want to change is the user details found inside of the configuration.nix. Here, you'll want to change the username from Elliot, replace the OpenSSH authorized keys with your own public key, and also change the hashed password. In order to replace the password hash, you can generate a new one using the makePassword command found inside of the Nix OS installer. Once you've created this new password hash, you can then copy it to your clipboard and paste it into the Nix OS configuration. As well as changing the user values, you'll also need to make some additional changes when it comes to the K3's token. This is also a challenge I encountered when I was setting up the homelab, as I struggled with how to securely set this token value. This token is used for authentication when a node tries to join a cluster, which means it needs to be kept secret and shouldn't be hard-coded. The correct approach would have been to use something such as SOPS Nix, and I'll probably do a video looking at it in the future. Instead, I did something a little more resourceful. First of all, I generated a new token using the pwgen command, making sure to set the length of this to 16. Using the -s option also makes sure this is going to be secure. Then I copied this token to my clipboard and hard-coded it into the token value, which I know I said I shouldn't do. However, as long as you make sure not to commit this to Git, then it should be fine. Then later on, once I had installed K3s on each of the nodes, I then removed the entire hard-coded token and instead replaced it with the token file option pointing to the following path. This file is found on each of the nodes after installation and contains the full value of the K3's token. This allowed me to commit my configuration without leaking my secret. Before doing that, however, I needed to make sure I was still using the hard-coded token in order to set up the nodes using Nix OS Anywhere. To do so, I used the following Nix command, making sure to pass in the correct Nix OS configuration, of which I've defined from the node's hostname, in this case homelab-0, and then passing in the node's IP. This command did take a bit of time, as it had to build everything from scratch on my host machine. However, using Nix OS Anywhere made the whole process a lot faster, due to the fact that the processor on my source machine is a lot more powerful. Additionally, these build artifacts would also be cached, meaning I didn't have to rebuild everything again for the other nodes. Once the installation was complete, the node automatically restarted and booted into the new operating system. Then, to confirm that everything was working, I accessed the machine using SSH and ran the kubectl getpods command to see if the K3's cluster was up and running, which it wasn't. At least, not on my first attempt. In fact, this took me a few iterations in order to get my Nix OS configuration correct. Eventually, I managed to get there, however, and I finally had a single node K3's cluster running. Next, I wanted to make sure I could access this cluster on my host machine. So I copied over the Kubernetes configuration into the correct directory using the scp command. Then, opening it up in my text editor, I changed the value of the server from the loopback IP to homelab-0. After doing so, I then tested my configuration using the kgit nodes command, where k is an alias for kubectl. Once I had confirmed that everything was working, I then went into my router configuration and set the IP for this device to be fixed. This would prevent the IP of the node from changing, which could potentially cause issues. Lastly, I then created a sticky label for this device with its host name and stuck it onto the node. This allows me to easily identify which node is which in case there's a problem. With my first node complete, it was time to set up the next two. This was a very similar process of plugging in the various cables and the USB installer before turning it on, setting the password and obtaining the IP address. Then I could run the NixOS Anywhere command again, making sure to select the correct host/config name for the node, and using the correct IP address. As I mentioned before, both of these times it was a lot quicker to install. One of the benefits of using NixOS Anywhere. Once both of these installations were complete, I checked that everything was working by again using the kubectl getNodes command, which showed me that all of the nodes were in the ready status. So I labeled each of these nodes with their host name, then made sure to fix the IP address for each one. So far, my cluster was in a good state, but my desk certainly wasn't. So I spent a little bit of time tidying things up, moving the nodes into my already crowded server rack. With the nodes in their new location, and after confirming that my cluster was still working, I then moved on to setting up necessary services on my Kubernetes cluster. My main goal was to get an instance of Pi-hole up and running, configured in such a way that I could access it on my local network at the domain name of piehole.home. To be able to do so, I needed to add a container storage interface into my cluster, with my preferred option being Longhorn. Longhorn allows you to use the storage of the node in a distributed way, which helps to provide fault tolerance and redundancy for your data, and is one of the reasons why I wanted to go with a 2TB SSD on each node. My preferred approach for installing Longhorn, as well as many other services, is to use Helm, which is sort of like a package manager for Kubernetes. Rather than installing Helm charts ad hoc, however, I instead like to install them using Helm file, which provides a declarative specification for deploying Helm charts onto your cluster, sort of like infrastructure as code. To set up a Helm file, I created a brand new directory and a new file inside called helmfile.yaml. Then I opened this up inside of my text editor. I first needed to define the repository of the chart. Then I could define the releases block with my chart inside of it. In this case, I'm setting the name of the release to Longhorn, the namespace for this release to be installed as Longhorn-system, the actual chart to be Longhorn/Longhorn, which is the repository followed by the chart name. Finally, I like to pin the versions of my charts to make sure that they're reproducible, so I set this to be the latest version at the time of recording, which I was able to determine using the Helm CLI with the following two commands. First adding the Longhorn repo and then searching through it. With my release defined, it was now ready to be applied. First of all, I needed to install the Helm file binary onto my system, which I did using Pacman. Additionally, Helm file also requires Helm to be installed, which I went and double checked. In order to install the necessary plugins required to make Helm file work, I used the Helm file init command and selected yes for each of the prompts. Afterwards, I then used the Helm file apply command to deploy my chart to the cluster. This then created the necessary resources required by Longhorn. And once it was done, I could then check if everything was working by using the following kubectl command, which unfortunately it wasn't, as the Longhorn manager pods were in an error state. In order to determine what the error was, I checked the logs of one of the pods, which indicated that the iscsi admin binary was not installed on the host. This binary is a required dependency of Longhorn in order for it to work. But when I SSH'd into one of my nodes and ran the following command, there it was. The reason that Longhorn couldn't find it, however, was due to the fact I was running NixOS, which doesn't follow the standard file system hierarchy in Linux. Fortunately, I wasn't the only person who encountered this problem, and there was an issue on the Longhorn GitHub repository which had a simple fix. So I added this fix into my NixOS configuration and went about redeploying it on each of my nodes. To do so, I first committed this change and pushed it up to my remote repository. Then I SSH'd into each one of my nodes, pulled down this repo and used the following command with the respective hostname in order to rebuild the NixOS system. Once it was complete, the failing pods were then working and Longhorn was up and running. With my container storage set up, the next thing to configure was the ability to hit services on my cluster via an IP. To achieve this, I use a load balancer, specifically MetalLB, which provides a load balancer implementation for bare metal Kubernetes clusters. To install it on my cluster, I again use the Helm chart, adding the details into my Helm file. Then I used the Helm file apply command to deploy it onto the cluster. Doing so created the MetalLB namespace, which contained the MetalLB controller. With both the container storage and load balancer set up, I was now ready to deploy Pi-hole. If you're unaware, Pi-hole is a DNS server for your local network, which can allow you to easily register local DNS records, as well as performing network-wide ad blocking. For me, I mostly use it so that each of my services on my cluster has a local DNS record, which I find is a much better experience than trying to remember an IP address. As there's a nice Helm chart available for Pi-hole, I added another entry into my Helm file releases. However, for this chart, I also needed to add some additional configuration. In Helm, the best way to do this is by using a values file. So I defined this values file inside of my Helm file and went and created it. Inside, I added in the following configuration to ensure that there was a persistent volume, and the load balancer IP for both the web and DNS services would be the same, which was 192.168.1.250. Again, all of this is available on the video's GitHub repo. With my values defined, I could then use the helm file apply command to deploy my instance of Pi-hole, and after a short while, the Pi-hole pod was running inside of the Pi-hole system namespace. Additionally, the Helm chart had also managed to create a persistent volume using Longhorn, showing me that everything was correctly configured when it came to my container storage. However, when I checked the status of my load balancer services, the external IP was still in a pending state. This was happening because I had forgotten to declare an IP pool on Metal LB. In order to resolve this, I needed to create some Kubernetes manifests based on the custom resources that Metal LB provides. When it comes to individual manifests in Kubernetes, I like to manage these using Customize. So I created a new directory to store these manifests in and defined my customization.yaml. Then I defined the resources that this customization was going to manage. In this case, that was a single file at the path metallb/pool.yaml. After defining my customization, I then went and created this file. First, defining the IP address pool as follows. For the IP addresses, I specified a /26 CIDR block of 192.168.1.192, which defined the following IP range. In my router's DHCP configuration, I had also made sure to exclude this range from being auto-assigned, helping to prevent any IP collisions from devices on my network or Metal LB. Underneath the definition for my IP address pool, I added in another resource of an L2 advertisement, pointing this to the IP address pool I had just created. With my manifests defined, I could then apply my customization using the following kubectl command, and after a few seconds, my Pi-hole services now had an IP associated with them. To test that it was working, I opened up my web browser and headed over to the URL for this IP at the /admin path. This brought me to the login page for Pi-hole, which requires the password of admin by default. You can determine what this password is by using the following command to access the Pi-hole secret, then copy the value to the clipboard and base64 decode it. With that, Pi-hole was up and running. But before I could use it, however, I quickly made the change to point my upstream DNS servers to my router's IP address, so that I could still access the computers on my network with their hostname. Unfortunately, when using the Helm chart, setting the DNS records this way presents a problem. If I go ahead and restart Pi-hole by deleting the pod, when it starts back up again, the upstream DNS record that I set is cleared. When it comes to this Helm chart, the correct way to configure it is by setting it in the Pi-hole's values.yaml, which is done by adding in the following lines. Then by again running helm file apply, the DNS configuration is now set and my router acts as the upstream DNS server. Next was to set Pi-hole as the DNS server for my local machine. I achieved this by using the Network Manager CLI, typing in the following commands. Now, when I run nslookup, we can see that it's using my Pi-hole DNS server. With both Pi-hole set up and my machine using it, the next thing I wanted to do was make it available to access on my local network at the domain of pi-hole.home. The easiest way to do this is by adding in a DNS record to Pi-hole. But doing this manually defeats the point of using Kubernetes. Instead, I can automate this by installing a couple of other things onto my homelab. The first of which is the Nginx Ingress controller, which allows us to create Ingress resources powered by Nginx. When it comes to Kubernetes, you can think of an Ingress controller as being a reverse proxy for the services in the cluster. For this chart, I also wanted to add some additional configuration inside of its values file as well. This was to make sure that this resource was set as the default Ingress for the cluster, and to also specify the Ingress class and name as Nginx-internal, just to signal that this Ingress controller was only meant for my local area network, i.e. internal to my LAN. Once the chart was defined, I could then use the helm file apply command, and after a short while I had an Nginx controller inside of the Nginx system namespace. With the Ingress controller installed, the next thing to do was to set up an Ingress resource so that the piehole.home DNS would point to my Piehole service. Rather than having to create this myself, however, the Piehole Helm chart comes with its own Ingress option, meaning I was able to define the Ingress inside of the values.yaml. So I headed on over to the Piehole values file and added in the following configuration to enable an Ingress and to set the hostname to piehole.home. With these changes made, I went and performed the helm file apply command again. And after a short while, an Ingress resource was available inside of my Piehole system namespace. However, whilst I could hit this using curl, I still didn't have a DNS record pointing to my Piehole instance. For that to happen, I needed to use one final chart, external DNS, which we can use to automatically write DNS records to our Piehole server based on any host names found in our cluster that are associated with the Ingress controller. To set this up, I began by adding in the chart to my Helm file, followed by defining a values file in order to set up any custom configuration. Here I set up the DNS server that external DNS should write to be the Piehole instance we had already set up. Then when it came to detecting host names, I configured this to only check for those found inside of the Nginx internal ingress, which was achieved by adding nginx-internal to the ingress class filters property. All that remained now is to run the helm file apply command one last time, and the external DNS service was up and running. When I checked the logs, I could see that it had written a DNS record to Piehole. And when I opened up the Piehole server, there it was. Now I could access my Piehole instance using the piehole.home domain name. With that, I had my basic services set up on my homelab cluster, and I was ready to start migrating the rest of my services. I'll plan on looking at some of those in further detail in another video. So if that's something of interest, then let me know in the comments down below, and I'll bump it up to the top of my priority list. Otherwise, I hope you both learned something and enjoy the video, and hopefully I'll see you on the next one.